Students, and till now we've learned about charges, how they behave in the vicinity of one another. We know that positive charges, when close to another, they will try to repel each other, right? So they will exert a force in the opposite direction, try to stay away from each other, right? The same case is with the negative charges. When you try to put them closer to one another, they will try to just stay away from one another, right? But what happens with the opposite charges is that they try to attract one another, right? They try to come closer to the other side, to the other charge, because of their opposite polarities, because of their opposite charges. Okay, so but we have to just know that by how much force will they attract or repel each other. So Charles Augustin de Coulomb in 1785 discovered this law, gave this law, which is known as Coulomb's law. This law is really important from the paper point of view as well, so you really have to understand it briefly. Okay, so it says that like charges repel and opposite charges attract, as we have already studied earlier, with a force proportional to the product of the charges and inversely proportional to the square of distance between their centers. Now this thing is kind of new to us, right? So what does it mean by the force proportional to the product of the charges? So mathematically we can write it as the force which is proportional to the product of the charges, the two charges, and inversely proportional to the square of distance between their centers, and is inversely proportional to the square of the distance. R defines the distance between their centers. Remember that we don't have to take distance from here, from the surface of this charge. Okay? We have to take the distance from the center of this charge, right? The center of these charges. So I have just drawn two charges. This one is positive charge and this one is negative charge. So obviously they're gonna attract each other, right? We call this one Q1 and this one as Q2. So what are they going to do? They're going to attract one another with a force which acts along a line joining them, right? So the force won't act like this or this or anything like this. It will be directed straight from the center of first one to the center of the second one, or from the center of the second one to the center of the first one. Okay, so this force acts on the line joining the centers of the charges, right? R is the distance between these charges, right? F2, F21 and F12 are the forces applied by this charge and this one. Now the F21 is the force applied by FQ2 on Q1, because the subscript comes first, so it means that the Q2 charge has applied the force on charge Q1, and F12 as the subscript 1 includes is that the Q1 charge apply a force on the Q2 charge. So Q1 is the charge that will be going to apply the force here, right? So these forces are vector quantities, obviously, because they are directed to some specific direction. The same case is with same charges. I've taken the positive charges. You can also take negative charges, but they should be the same polarities, right? So here we have Q1 and Q2, and again F21 and F2. The only difference is that is of direction. Okay, there lies the case of repulsion. So this force will be directed away from this charge, and this force will be directed away from the charge Q1. So this proves our Coulomb's law. It says that the force is directly proportional to the magnitude of these charges, that how much charge these masses carry, how much is the intensity of this charge, right? And is inversely proportional to the distance of, to the square of their distance, right? So if we increase the distance between them, obviously the force is gonna just put down, right? It is gonna decrease in nature. So if we just increase the radius a little bit, these forces are gonna decrease by the square of that radius. Okay, so these are very critically dependent upon the radius or the distance between them, right? Now we're going to mathematically combine these two equations as if one quantity is proportional to something and is proportional to something else, then we can just combine these two proportionalities into one equation. F is directly proportional to Q1 Q2 divided by R square. That is what we've got from these two equations over there. Okay, now just getting rid of this proportionality sign, we're gonna get a constant over here. Okay, if we remove this proportionality sign, we're gonna get F equals to K Q1 Q2 by R square. This is our final equation, and this is a you can say most important formula for electrostatics for your book. Okay, so this is the equation for Coulomb's law. This is the mathematical representation of Coulomb's law. Okay, it says that F is equal to the magnitude of product of these two charges and divided by square of radius to some constant K. What exactly is this constant K? K is the Coulomb's constant or constants of proportionality. You've already studied about constants of proportionality, but here it has a name. It's called Coulomb's constant, and it has a value of 9 into 10 raised to the power 9 Newton meter squares per Coulomb squares. Okay, Newton meters for the charges and Coulomb square for per Coulomb, right? It can also be calculated using K equals to 1 by 4 pi epsilon naught. So this is kind of new to us. We have studied about constant earlier. We've studied about charges. We have studied about the distance between them. But the new thing is this K constant and 1 by 4 pi epsilon naught. Okay, we call this as equation number 3. So where epsilon naught, I'm going to just write over here epsilon, right? It's just an alphabet, Greek alphabet. So we write the lowercase epsilon. Here we have a little over here to just demonstrate or describe that this is the epsilon, or we call it permittivity of free space. This little o is for free space, right? So that we can distinguish it from the other simple epsilon, right? This is called the permittivity or simply epsilon of free space. So the greater the permittivity, the weaker will be the force. Why? Because here you can see the permittivity of free space is in the denominator. It is inversely proportional to the K. If it's inversely proportional to the K, so increasing the permittivity would decrease the K. Decreasing the K would result into a lower force. Okay, a weaker force, of course. We should draw an arrow over it. Okay, to show that it's a vector. Alright, so K equals to 1 by 4 pi epsilon naught. You can actually put values of epsilon naught for pi to this equation and get 9 into 10 raised to power 9 as a result. If in numerical problems you are not given any other value of epsilon, then you are just going to put 9 into 10 raised to power 9 in place of k. You don't have to actually calculate everything over here, okay? So if you are not given any other permittivity, then you are just gonna use 9 into 10 raised to power 9 for the k. But what happens if we don't have free space? We are using some other material medium like air or water or glass or etc. or anything else. So what happens if you're gonna use the permittivity other than the free space? The permittivity of air is much more than that of the free space, right? So the permittivity vacuum has a permittivity less than air or water, or air or water has a permittivity greater than that of the vacuum. So for any medium other than vacuum, permittivity becomes epsilon, right? So this is a difference between epsilon naught. Epsilon naught just indicates that this permittivity is for free space, and for any other permittivity, for any other material, we use the symbol epsilon naught, and this value should be given in your numerical problems. All right, so you don't have to memorize the epsilon naught for every water, air, glass, meat, etc. This should be given in your numerical problem. So that's basically a constant, and k can be written as now k equals to 1 by 4 pi epsilon, because we are not using epsilon naught. We are not using vacuum over here, okay? So in case of any other material medium other than vacuum, we use this equation, and for the case when we use free space or vacuum, we are gonna use this one, right? And if we are not asked to explicitly calculate these things, then we are not just gonna use this. We are gonna use the 9 into 10 raised to power 9 in place of k and calculate our force of attraction or repulsion. Remember that whenever you just try to solve these kind of numerical problems, you have to just make sure to use the right magnitudes. All right, this is not dependent upon the sign, right? This is the magnitude of these two charges. So if you are using electron, you don't have to write a negative sign over here, because these are the magnitude. It has nothing to do with the direction. Even if you put the negative sign, it has to be removed away from here, because this force won't be proportional to the sign of these charges, or the polarities of these charges. Okay, so it's just dependent upon the magnitudes. All right, so this is all about the Coulomb's law. Always note that there should be some there are some points to be noted over here. So first thing is, Coulomb's law is applicable on the charges which are very small in size. All right, so the charges which are very small in size, we call them point charges, because they are very small as compared to the distance between their centers. Okay, so Coulomb's law is applicable in the case when these charges are very small and the distance between them is large as compared to the size of these charges, right? So I'm just gonna write it over here, okay? Size of charges should be small as compared to the distance, right? The second point is this Coulomb law is applicable to stationary charges. So you might think that what kind of charge is a stationary charge? Actually, even a proton or the nucleus, which has a positive charge, Even nucleus is in motion and the electrons are always in motion. So what exactly are these stationary charges? You might think of that. And actually in practical life, the stationary charges don't really exist. We cannot have a charge which is just at rest. So the charges which are moving with constant velocities and they don't switch to the other shells, like this one, like I'm gonna draw an atom over here. This is the nucleus, these are the electrons, right? If these electrons are moving with constant velocities and they're not jumping to other shells or other orbits and they are continuously revolving around the nucleus, then these electrons will be called as stationary. Alright, if they're not accelerating, they're not producing an external electric field, then these will be called as stationary charges. And Coulomb's law is applicable to these kind of stationary charges. If it's not moving with constant velocity, it's accelerating or leaving its shell, then the distance between nucleus and the charge would change and Coulomb's law cannot be applied to this charge. Okay, so this is just for the charges, the stationary charges, the ones that do not change their state. All right, so point number 2 is that applicable to stationary charges only, right? Alright, so these 2 points are something that you really need to remember. You can also include a point that you are always going to use the magnitude of these charges. Okay, you're not going to actually include the signs of these charges. Okay, so this was all about Coulomb's law. Thank you so much, everyone.